Hey everyone, in today's video we're going to be solving the problem delete node in a BST. So the question says given a root node reference of a BST and a key, delete the node with the given key in the BST and return the root node reference of the BST. Basically, deletion can be divided into two stages: search for a node to remove, and if the node is found, delete the node. Cool. So this is what the question is, guys. Now, let's say you're given a BST like this. Right. Now, what the question says is that you're given a BST and you're given a key value like this over here, 6. Right. And you need to find this 6 in the tree and delete it. Right. And you need to delete it in such a way that the property of BST that left node is less than nodes, that the root nodes are less than the right nodes. This property is maintained. So basically, everything on the left, so if 10 is a root node, right, let's consider 10 are root nodes. Everything on the left of 10 is less than it, and everything on the right of 10 is greater than it. So this should be less and this should be greater, right? So this property of the tree should be maintained. Right. Now, if I delete 6 over here, right, what's going to happen? So if you delete 6 over here, let's just delete this, right? If 6 is deleted like this, right, you can see that you have two remaining trees, small trees basically. You have one tree of just 7, and you have one tree of 3, 2, and 4. And you have one pairing tree from which 6 was deleted, this one, the 10 one, like this one basically. Right. So you have three trees. Right. But you need to connect all of them in such a way that the property of BST is maintained. Now, these two trees, 7 and 3, 2 and 4, need to be connected to this main tree. Right. And you need to connect in such a way that BST is maintained. So how are you going to do it? Now, it's not like you can just add one tree and leave one portion of it out. Everything needs to be connected, right? Now, 6 was over here. This is the left of 6, and 7 was the right of 6. Right. So these are the left nodes and these are the right nodes. So how are you going to connect these left nodes and right nodes? Right. Now let's look at it logically. What we can do over here. Right. Let's just remove all of this. So 6 is out. And let's write this again: 3, 2, 4, and 7 a bit properly. So let's say we had 3, 2, 4. Right. And let's say we have a 7 over here as well. Right. Now, what you can do is you can connect this 8. One thing let's do is let's connect this 8 to 3 over here. The left of 8, which was connected to 6, is now directly connected to this 3. Right. Now, this tree, if you look at it, is a BST, or the whole thing. This whole tree right now is a BST. Right. If you can see it, like 8's left is 3, which is 4 is greater than 3, and 2 is less than 3, and 4 is also again less than 8. So all of it is maintained. But what about 7 now? What we can do with 7 is, if you see over here, the 6, everything on the left of 6, which was 3, let's say everything on the left of 6, which is 3, 2, and 4, if you think about it, let's just write in a different page over here. So 6 was over here, you had 3, 2, and you had 4 over here, and you had 7 over here, right? If you think about it logically, right, over here, this portion of 6, you go to the very everything on the left of 6 is going to be less than 7, because 6 itself is less than 7, right? So if you look at the very greatest value of left of 6, which is 4, right, which is logically supposed to be 4, right, it is on its own less than 7, right? So what you can do is, what if we just remove this 7 from here, right, and just connect it over here to this portion? Would this balance out the BST? Let's just remove this 6 as well. You need to make it like this. So if it's going to be like this, let's go to the previous page over here. So if it was like this, and if we connect the 7 to 4's right, would the BST be maintained? Yes, the BST would be maintained, because 8 over here is greater than 7, right? 8 is greater than 7, 8 is greater than 7, right? And 7 is greater than 3, 2, 4, and it's on the right of it, all of them, right? So all the properties of BST is maintained if you look at this tree as well. So this is one way on how you can connect it. Now, another way on how you can connect the tree would be logically just, let's just remove all of this. One second. So let's say you have 3, 2, 4, and 7, right? Now, what if I just connect 7 over here, right? 7 to 8. What's going to happen now? If you connect 7 to 8, now let's go to that page again and see over here. If you had a 6 over here, right? And if you removed 3, 2, 4, and 7 like this, and let's say, let me just write it again. you had 3, 2, and 4, and you had a 7 over here. Right. Now, if you think about it, if you see over here, is everything on the right left of 6 less than 7? Then yes. And if you had something like, let's say you had an 8 over here and you had 7 here and you had a 6 over here, is everything on the very left of the right of 8, right? Is everything on the right of 8, the most leftmost element, which is going to be 6 over here, right? The most leftmost element on the right of 8, which is 6 over here, is it greater than everything on the left of 8 over here? Yes, it is less, right? So everything is less. So what you can just do is you can just traverse to the most leftmost node in the right tree, over here. What we were previously doing is we were traversing on the left node over here, the left node's rightmost node. And in this case, what we're traversing, when we check over here, we're going to right node's leftmost node. And we're just seeing that the left node over here, which is 6, is greater than everything on the left. So what we can easily just do is we can just take all these nodes. Let's just remove everything. And what we can do is if we have a 7 over here, you can just connect everything to the right of it like this, 3 to the left of it like this, 3, 2, and 4. And the property of BST again would be maintained. So if you go back to the previous page over here, and if you connect everything like this, 3, 2, and 4, again, the whole property of BST is maintained, and this tree is a binary search tree, right? Everything is maintained, and this is how you're going to solve the problem. Now, let's say we just have, let's say, one small edge case over here, right? Let me just remove everything like this. And let's say we have something like, a 5, we have a 3, and we have let's say 4, right? Now, the key to remove in this tree, let's say, is 3, right? Now, if I remove this 3 over here, what can happen, right? We need to connect, because there is no left node over here, right? Let's say we're traversing through the very first approach which we did. We traverse to the left node and we connect the remaining left nodes to the main tree, right? If we do that, right, because we're going to be following that approach, because and if we do that, okay, and it's not the case for the it's not like it's not going to be the same case for the right tree, right? It's the same, mostly same. It's basically the same thing applicable to the right tree as well. But let's look at for the left tree. If there's no left tree available over here, so we can't connect anything to 5 over here, right? So what we're going to do is we're going to check if this node is null or not. So is the left of 3 null? If it is null over here, right? If it is null, what we're going to do is we're just going to take the right and we're going to connect it to 5 over here. So we have 4 on the right of the tree. So we're just going to take 4 over here and we're going to connect this to the left of 5 like this. And this is going to be a tree, how we're going to make it. So this is only one small edge case for this problem. All right, guys. So this is how we're going to solve the problem, guys. And let's just look at the code now. So this is what the code of the problem is, right? Let me just, make this like this. And yeah, this is the code for the question, guys. So these are two helper functions we have over here till here. And this is where the main code starts. All right. Now let's just do a dry run of the code once. Right. So let's say we have okay, let's just take the code, and yeah, this is the code, and let's just do a dry run on this question as well. Again, let me just remove everything over here. Let me just remove all this. Okay, and okay, let me just remove this as well. Right, let me just make the tree again. This is 6, this is 7, this is 3, this is 4, and this is 2. Right. And let's say this is I think 50. Right. So if this is your tree now, right, the very first thing what we're doing is we're checking if the true tree is null or not. The main thing is just check whether if it's null, just return none. Right, this line. If it's none, just return none. Right, because there's no tree, then you have no output. Now, in this case, if root.val is equal to key, return helper of root. Right. If your root.val, basically if 10 is equal to basically if this 10 was the key, right? If this 10 was the key for the question, what we would have done is we would have just followed the helper function. Now what the helper function is going to do is just going to go inside and do whatever I just explained to you right now. We'll just get into that in a short while. Let's just go forward now. Now with the question, now what we're going to do is we're going to make cur equal to root. Why are we going to make cur equal to root? Because we're going to make changes to root, and we want to return the main root in the question over here, which it says that return the root node reference possibly updated of the BST. So you need to update the tree and return the main head node of it over here. So we're just going to make that cur, and so that we return cur in the end. Okay. Now, while root, okay, we're going to loop until we have values in the root, until it's not equal to none. We're going to check if root.val is greater than key, right? Is our 10 greater than 6? Okay, is 10 greater than 6? Let's say here, is 10 greater than 6? Yes, 10 is greater than 6. So what we're going to do is we're going to go inside this loop, this over here, and we're going to check if root.left is not equal to none, and if root.left.val is equal to key. Is my 8 over here equal to none? No, it's not equal to none. And is my root.left.key, let me just undo this, is my root.left.key, which is 8, right? This root.left.key is 8. Is it equal to 6? No, it's not equal to 6. So what we're going to do is we're going to go to the left of it, right? Root is equal to root.left. So we're going to just jump over here. Now root was 8. Now we're going to make root equal to 6. Actually, we were at 10. We're going to jump at root equal to 8. Right now, our root is equal to 8. This is our root. Okay. Now, what we're going to do is again, we're going to check if root.val is greater than key. So is 8 greater than 6? So yes, 8 is greater than 6. So if 8 is greater than 6, we're going to go inside this loop over here, this whole thing. And what we're going to do is we're going to check if root.left is not equal to none and if root.left.val is equal to key. Now, is root.left.val, so the root.left is not equal to none. So 6 is not none. And is root.left.val. So is 8's root.left dot val, which is basically 6, because root dot left is 6 and root dot left dot val is the value 6 basically, right? Root dot left is the node 6, this node, and the value inside it is 6. Is it equal to the key value we have? So yes, it is equal, right? One second, let me just remove all the clutter I did over here once. Okay. Yeah. Yeah, it is equal to 6. So what we're going to do is we're going to go inside this helper function over here. Root.left is equal to helper root.left. Now, when we go inside the helper function over here, what we're going to do, let's just jump over here. This is the helper function. Firstly, what we're going to do is we're going to check if root.left is equal to none. Right. If root.left is equal to none, we just return a root.right. The thing which I previously explained to you guys, that if you have something like this, right? If you have something like 5, 3 and 4, if root dot left, because we're going to attach the left tree of this removable node, we're not going to attach the right tree, we're going to attach the left tree of the removable node. If this is equal to none, we're just going to return 4 over here, which is root dot right directly is connected over here, right? So this is what we're going to do, this is what it's going to do. So if it has no node, we're just going to return the root dot right of this, and we're going to go forward. Let's just go to the previous page now, right? We're going to do that, right? And again, over here, root dot, if is root dot left equal to none, so it's not none. So, right, it has a value on the right, it has a value on the left. So it has two values again. So what we're going to do if it has two values is we're going to check what the current right value is. The current right value is 7. So this is going to be my cur right. Right, this is going to be my cur right. And what the last right is going to go and do is we're going to find the very last left right root element. So we're going to go to the left tree on this, and we're going to find the very last right node. I'm sorry, guys. We're going to find the very last right node in the tree. Right. We're going to traverse like over here. We're just going to traverse in a very simple way. We pass it in a function. We're going to check while root dot right is true. While we have a value root dot right present, we're just going to traverse root is equal to root dot right. Over here, we're going to pass a root dot left over here because we want to traverse in the left tree over here, right? Because we want to traverse in the left tree, which is this, we're going to pass root dot left. In this case, we passed root r is 6 because over here we passed Our root is 6. One second. Our root is 6 because over here we passed helper with a root dot left, and root dot left is going to be the root over here. And since root dot left is the root, this is 6 is going to be our root right now. Okay. Now our current right value is root dot right. So our 7 is our current right value. So let me just write it over here. Let's just write it over here. Cur right is equal to 7, right? Is equal to 7. Now, if it is equal to 7, and last right is going to find the very last element. Last right is going to find the very last element in the right tree, right? So we're going to take 6. We're going to go to its, leftmost tree. We're going to go to the left tree over here, and we're going to find the rightmost element inside it, which is going to be 4, and we're going to assign it a value of, last right, like this, last right. Okay. Now, when we do all of this, the next step is we're just going to make last right's right value equal to current right. Right. So last right is 4 and our current right is 7. So what we're going to do is we're going to just take last right over here. Let me just, declutter this a bit. So let's go to our eraser. Just remove all of this thing over here. Let me just write it again. So we had, okay, so yeah, we had a 6, we had a 3, 2, 4. Right. Now, as you saw over there, our last right was 4. Let me just write this over here again. So our last right was equal to 4. Right. And what we're doing is we're connecting last right's right value equal to cur right. So what we're doing is we're just attaching 4's right to 7, which is our cur right now. Right. So we're connecting the right node of 6 over here to the right node of 6, which is 7, to the left's node, very rightmost node, which is 4. Right. When we connect it like that, we're just done. And what we do is we just return root dot left. And what is our root dot left? Our current root was 6 in this case when we passed it, and we just return root dot left, which is 3. So basically, what we do is we just remove this node over here. This node is basically kind of just removed, and when we return it, this helper function has root dot left equal to, because we return a root dot left when we pass 6, the left value which is going to get returned is 3. So this is going to be the returned node for us, like this. Let me just make it a bit better. Like, let me just write it in a bit better way. So this is going to be like this: 3, 4, 7, and 2. This is what the tree is going to get returned. And yeah, that's basically what we're doing, guys, in this question. I hope, and this is what this is what the same case is if you do it. If you're going to check if the root node was greater. Let's say if our root val was lesser than key, right? If our root key was something like 12 or something, you would have followed this approach over here, down here, right? And it's the same thing. The whole process is the same. You just write it in on your own. But this is how the problem is, guys, and this is how you're going to solve the problem. And yeah, that's all for today's video, guys. So if you like the video, do like, share, and subscribe. Do let me in the comments if you have any more, if you have any doubts or if you have any suggestions for how I can make these videos much more better. And yeah, do check out my podcast. Do let me in the comments if if you didn't understand anything. And yeah, let me just run the code once. Yeah, it's running. Let me just show you. Yeah, it's running, and let's just submit this. Yeah, it's getting submitted as well. So yeah, guys. And for the time complexity of the code, let me just write in a new page or something over here. So the time complexity of the code TC is equal to O of h, where h is the height of the tree, right? Of the tree. Okay. So this is what the question is, guys, and this is how you solve the problem. Thanks for watching.